The evolution of artificial intelligence from rule-based systems to deep learning. Artificial intelligence (AI) has undergone remarkable evolution since its inception. What began as simple rule-based systems has blossomed into the complex and powerful deep learning models we use today. The journey of AI's development is not merely a technological advancement, but a shift in how we understand intelligence, learning, and problem-solving. This article explores the progression of AI, from its early rule-based foundations to the cutting-edge deep learning systems driving modern advancements. 1. Early days of artificial intelligence, rule-based systems. In the mid-20th century, AI was born out of the desire to replicate human-like intelligence in machines. The early approach to AI was based on symbolic reasoning and logic, where machines followed predefined rules to perform tasks. These systems, known as rule-based or expert systems, were designed to simulate the decision-making process by applying explicit knowledge in the form of if-then rules. The knowledge was typically encoded by human experts who could define all possible inputs and their corresponding outputs. One of the earliest and most famous rule-based systems was ELIZA 1966, created by Joseph Weizenbaum at MIT. ELIZA was a natural language processing program that used simple pattern matching to simulate conversation with a human. Another early expert system, Mycin, developed in the 1970s, was designed to diagnose bacterial infections and recommend antibiotics. Mycin employed a set of rules to analyze patient symptoms and generate a diagnosis, proving that rule-based systems could be applied in fields like medicine. However, these systems had significant limitations. They were heavily reliant on explicit human knowledge, could not generalize beyond their predefined rules, and struggled with ambiguity or incomplete data. Despite these limitations, rule-based systems formed the foundation of AI research and set the stage for future developments. 2. The shift to machine learning, introduction of statistical models. In the 1980s and 1992, AI researchers began to recognize the shortcomings of rule-based systems. One major limitation was the need for extensive human input in encoding knowledge. Researchers sought a new approach that would allow machines to learn from data rather than relying solely on predefined rules. This marked the emergence of machine learning (ML) techniques. Machine learning is based on the idea that computers can learn from patterns in data and make decisions or predictions without being explicitly programmed. Early machine learning models, such as decision trees, support vector machine SVMs, and neural networks, introduced new possibilities for AI. These algorithms use statistical methods to analyze data and make inferences. For example, decision trees worked by splitting data into subsets based on feature values, and SVMs sought to find the best boundaries to classify data into categories. Neural networks, which were inspired by the biological structure of the human brain, were one of the most exciting developments in this era. They consisted of layers of interconnected nodes neurons that could learn to recognize patterns in data. However, these networks were shallow, had fewer layers, and struggled with scalability and performance on complex tasks. The introduction of probabilistic models, such as Bayesian networks, further expanded AI's capabilities, particularly in situations where uncertainty or incomplete information existed. These models allowed machines to make decisions based on the likelihood of different outcomes. Despite these advances, traditional machine learning models were still far from perfect. They required extensive feature engineering, manually selecting the right input variables, and they were often limited by the computational power available at the time. Yet, the groundwork for a new era of AI was being laid. 3. The rise of deep learning, revolutionizing AI. The real breakthrough in AI came with the rise of deep learning, a subfield of machine learning that uses deep neural networks with many layers, hence deep, to model complex patterns in data. While neural networks had existed since the 1950s, they were not widely adopted due to limited computational resources and insufficient data. The surge in deep learning success in the 2000s was driven by three key factors: the availability of large datasets, improvements in hardware, especially GPUs, and advances in optimization algorithms. One of the pivotal moments in deep learning's rise came in 2012 when AlexNet, a deep convolutional neural network (CNN) designed by Alex Krizhevsky, Geoffrey Hinton, and Ilya Sutskever, won the ImageNet competition by a significant margin. AlexNet demonstrated the power of deep learning models for image recognition tasks. The model's success was due to its ability to automatically learn features from raw data rather than requiring manual feature engineering and its use of convolutional layers to efficiently process images. Deep learning models, particularly convolutional neural networks (CNNs), recurrent neural networks (RNNs), and transformers, began to dominate a wide range of AI applications. CNNs excelled in computer vision tasks. RNNs were used in natural language processing (NLP) and speech recognition. And transformers revolutionized NLP with models like BERT and GPT. The key advantage of deep learning over traditional machine learning was its ability to learn complex hierarchical representations of data. For instance, in image recognition, early layers of a deep neural network might learn simple features like edges, while deeper layers learn more complex features like shapes and objects. This hierarchical learning allowed deep learning models to outperform traditional machine learning techniques in tasks involving large, unstructured datasets. 4 key milestones and breakthroughs in deep learning. Several breakthroughs further advanced the capabilities of deep learning. Convolutional neural networks, CNNs. CNNs revolutionized image classification and object detection. With their ability to capture spatial hierarchies and local dependencies in images, CNNs became the go-to method for tasks like face recognition, self-driving cars, and medical image analysis. Recurrent neural networks (RNNs) and LSTMs (RNNs) and their variants, such as long short-term memory LSTM networks, proved invaluable for sequential data like time series, speech, and language. These networks could remember previous inputs, allowing them to capture context and temporal dependencies. Transformers and attention mechanisms. The transformer model, introduced in 2017 by Vaswani et al., completely transformed the field of NLP. By using attention mechanisms, transformers could focus on different parts of a sequence, enabling parallelization and significantly improving performance on tasks like machine translation and text generation. Transformers led to the development of models like GPT Generative Pre-trained Transformer and BERT, which set new benchmarks for NLP tasks. Generative models, GANs Generative Adversarial Networks (GANs), introduced by Ian Goodfellow in 2014, were a significant innovation in AI. GANs consist of two neural networks, a generator and a discriminator, that compete with each other. The generator creates fake data, while the discriminator attempts to distinguish between real and fake data. GANs have been used to generate realistic images, videos, and even music. 5. The future of AI, beyond deep learning. While deep learning has brought about unprecedented success in AI, the future of artificial intelligence may lie in integrating different approaches, including symbolic AI, reinforcement learning, and neuro-symbolic systems. Deep learning models are still limited by the need for large amounts of labeled data and can struggle with tasks requiring reasoning, generalization, or common sense. Combining deep learning with rule-based systems, human-like reasoning, or learning from fewer examples may lead to more robust and generalizable AI systems. Moreover, the ethical and societal implications of AI are becoming increasingly important. As AI systems continue to evolve, questions surrounding privacy, fairness, accountability, and the impact of automation on jobs will require careful consideration and regulation. Conclusion: the evolution of artificial intelligence from rule-based systems to deep learning represents one of the most exciting transformations in the history of technology. Rule-based systems provided the foundational understanding of machine reasoning, while machine learning introduced the concept of data-driven learning. Deep learning, with its ability to process vast amounts of data and uncover intricate patterns, has led to breakthroughs in nearly every field, from healthcare to entertainment. As we continue to advance, AI will likely evolve beyond its current capabilities, blending human-like reasoning with deep learning's raw power. The future of AI holds the potential to solve some of humanity's most pressing challenges and unlock new frontiers of intelligence and creativity. However, with this power comes the responsibility to ensure AI is developed in a way that benefits all of society.